Hey there guys, welcome back. We're gonna take a look at some of the notes here together and we're gonna do some sketches. So here on the first slide, we're shown that not all organic molecules are straight chains. Oftentimes they branch out at 1, 2, or more places. In this case, 2-methylpropane, we see that there is a 3-carbon chain. We call that the parent chain, the longest undisturbed chain. A single carbon, the prefix you might remember is meth. When we're naming side chains, we always add a YL to the end. So it becomes a methyl side chain. If we take a look at our next example here, we've got 2,2-dimethylpropane. So we've got a propane, and propane, you got to remember, is 3 carbons long. It's the longest chain. It doesn't always have to be in a straight line. So for example, if you wanted the propane to be these 3 carbons, that can be your longest undisturbed chain. On this longest undisturbed chain, we have 2 methyl groups, or dimethyl. If we were to number our carbons 1, 2, 3, or in the other direction, 1, 2, 3, in either scenario, this is the second carbon. The second carbon, hence the 2,2-dimethyl. Each of the 2 methyl groups attach at the 2 position. So here's the strategies we use when we're naming or drawing these types of compounds. First, we get to identify the longest carbon chain. This will be known as the parent chain. In the name, it always comes at the end. Next, identify all substituent groups. They must end in YL to be a substituent group. A substituent group is another way of saying side chains. Next, each carbon of the parent chain must be numbered. We always number in the direction that gives us the smallest values in our name. So left to right or right to left, it depends where the side chains are. We always count in the direction that gives us the smallest numbers in our answer. An easy tip might be to add up the numbers. If there's more than one side chain, say 2, 4 or 3, 5, 2, 4 adds up to 6, 3, 5 adds up to 8. So 2, 4 would be the correct name. When we say add up the numbers, we mean the addresses for the side chains. All right, let's try one. We call this the parent chain. It comes at the end of a name. Let's draw this out. All right, so when we're drawing out our parent chain 1-decyne, we identify that YNE refers to a triple bond. The 1 in front of decyne tells us it is at the 1 position. Now let's fill in some of our side chains. 3-methyl, we have to choose a direction of numbering. Now our direction of numbering is actually already chosen for us here. If this is the first bond, that forces our numbering to be in this direction. So one more time, a functional group like an alkyne, a triple bond, determines the direction of numbering. So that would mean this would be carbons 1, 2, 3. So 3-methyl would be a 1-carbon side chain. 4,6-dipropyl, di means there's going to be 2 propyl groups. The first group is at the position 4, the second group is at position 6. Let's draw them. All right, all that's left now is to fill out our remaining hydrogens. These numbers here are all just part of, again, a hard time cleaning these up here. Those numbers for those carbons aren't actually part of our final answer. So let's make sure that we kind of get rid of some of these guys. All right, so that's an example of 3-methyl 4,6-dipropyl 1-decyne. Let's try another one. 3-ethyl octane. As always, we start by drawing the parent chain. Let's go. All right, next, at the 3rd carbon in the parent chain, we need to add an ethyl group. The prefix ethyl refers to a 2-carbon long chain. All right, let's fill out the remaining hydrogens. Awesome. Notice how I didn't count the carbons on the chain this time? That's something you can do in your head. The previous example, we counted all the carbons just for explanation purposes. All right, here we've got 3-ethyl octane. Something you might notice is that if the parent chain was actually this chain, 1, 2, 3, 4, 5, 6, 7, 8, we would still have a 2-carbon or ethyl group on carbon number 3. So in this case, don't be fooled by some questions that might have twists and turns. You got to find the longest chain of carbon, no matter what. Let's try one. All right, so here we've drawn a branching molecule, hydrogens all over the place. Maybe you think this is the longest chain, 1, 2, 3, 4, 5, pentane. I don't think so, though. What if this is the parent chain? Let's count it out. 1, 2, 3, 4, 5, 6, 7. There are 7 carbons in this parent chain. That makes it the longest undisturbed chain in this molecule. That means that our parent name will be heptane. Next, we have 2 side chains. We got to figure out at what position these 2 side chains are. Well, they're both methyl groups, so let's call them dimethyl. We need a number, don't we? If this was 1, 2, 3, 4, 5, 6, 7, that would make this 3,5-dimethyl. Let's count in the other direction just to be sure. Well, in this case, it would be still 3,5-dimethyl. So I think we're good on this one. When we look at oxalate and acetate, they both have strange formulas. Why don't we group all the oxygens together or all the carbons together? Very strange. These are condensed structural formulas. Let's draw out acetate. The OOCCOO tells us that these oxygens are independent of one another, and each are connected to the carbon. Now, if we follow the dot structures that we looked at last day, each of these 2 oxygens at the top have 2 bonds and 2 non-bonding pairs. That fits. But each of these oxygens have 2 non-bonding pairs, 1 shared pair, and then just 1 single electron. The 2 negative charges in the formula means that there are 2 extra electrons. And this is where the 2 negative charges of oxalate lie. Acetate begins with a CH3. Notice how acetate, this oxygen, has an incomplete octet or an incomplete valence shell. That's where the final electron comes in. To fill out those 8 outer electrons around that oxygen, that's where the charge comes from. So these names, oxalate and acetate, and their structural formulas are written such that we can infer their chemical structure from their formula. And that's why they're written the way they are. Now, no doubt at this point, you're tired of drawing H's. There's just so many H's. You get one of those big, long, you're drawing H's, and then your hand cramps up, and then your H's start to not look like H's anymore, and it's just a whole big thing. What we've been doing is the expanded structural formula. Every carbon has exactly 4 bonds, no more, no less. Every hydrogen has exactly 1 bond, no more, no less. Now, if you feel like, yep, you're good to go, you know when a carbon is going to have 2 hydrogens attached, 1 hydrogen attached, 0 hydrogen attached, whatever. If you know that, because you've been practicing, then you can move on to the condensed structural formula. In this case, rather than drawing each hydrogen independently, we list a summary. There's 4 on this carbon. For this first carbon, there's 3 hydrogen attached, CH3. This carbon in the middle here, it's got 2 hydrogens on it, CH2. No doubt you see how the condensed structural formula is the best way to go. The only issue is, here we can check our work. Here, it's harder. Check our work. Just be cautious. I prefer the condensed structural formula personally. In addition to the condensed structural formula, Here we see a compound. Well, actually, let's name it first. So in this case, we have a 6-carbon chain, we would call hexane. And then we have a pair of groups. We have a methyl on the 2nd carbon, and we have an ethyl on the 3rd carbon. Now, E before M, the ethyl group, alphabetical order. This would be 3-ethyl 2-methyl hexane. And this is 3-ethyl 2-ethyl hexane, condensed formula. I don't recommend the skeletal structure right away. I think it's more important to get some practice and some thinking in about where the hydrogens are placed. This is more an expert level way of describing this structure, whereby you would intuitively know how many hydrogens are present on this molecule. Not all of us, I think, are quite ready there yet. In this sense, each vertex in the parent chain represents a carbon. 1, 2, 3, 4, 5, 6. There are 6 vertices on this line, just like there were 1, 2, 3, 4, 5, 6 carbons in the parent chain. There is an ethyl group on the 3rd carbon. There's 2 points, 2 vertices, and a methyl group on the 2nd carbon. This is the skeletal structure. Any of these 3 ways of expressing these structures are completely acceptable. That being said, I think we should be using the condensed structural formula. I don't know if we're quite ready for this one just yet. When we ask you to interpret that formula, how many hydrogens are there, it might be a challenge. We might make mistakes, and I think our goal is to try to avoid mistakes. Lastly, a structural formula. So in this case, we've got CH3 at one end, a CH3 at another end, and a whole bunch of CH2s in the middle. We have 1, 2, 3, 4, 5, 6 CH2s in a row, sandwiched between the CH3s. This is a condensed structural formula. Any repeating subunits are put in brackets, and how many there are in a row, listed afterwards. If you're going to do side chains, we would have to notice that here we've got a pair of CH3s. We have a CH, and then a CH3. So we have this CH is attached to a pair of CH3s. So we have CH3, CH3, CH. What we're supposed to infer from that is that both of these methyl groups, which each can only form 1 bond, attached to this carbon, which has 1 additional bond to continue the chain. Because we have a pair of CH3s, here they're grouped together. Again, this is some higher level stuff. Any of these answers would be pretty good. The only thing that I would maybe have an issue with is if you said this was the structural formula, because this has, whereas this has only 1 structure is possible. All right, and that's it. We've got a couple practice assignments to draw and name compounds. Please attach them to your assignment, submit for review, and make corrections as needed. Good luck, everybody. Have fun.